Hey everyone, welcome back. In this final video on surface integrals, we're going to start by taking a look at surfaces that can be represented by functions of two variables. So we've looked at these before in a couple of different contexts. So let's say we have a surface that we can solve for z. So it can be represented by a function of x and y. Then this ru cross rv, these cross product of partial derivatives, can be represented this way, and we've done this cross product before. We did this, one of the very first things in section 16.5 was computing this cross product. So it's the negative partial derivative of g with respect to x, the negative partial derivative of g with respect to y, 1. So that's going to be our normal vector. Not the unit normal, just the normal vector. Remember, we don't have to divide by the magnitude. It ends up canceling out. We just compute the normal without dividing by its magnitude. Now, if we have that the vector field we want to integrate can be represented by these component functions, p, q, and r, so these are functions of three variables. Then the flux integral, the integral of f dot n over the surface S, d sigma, can be represented by negative p, that's the first component function, times the partial derivative of g with respect to x, minus q times the partial derivative of g with respect to y, plus r. Now here d is a region in the xy plane, and dA is dx dy. We're integrating with respect to x and y. So we're assuming that p, q, and r, which are functions of x, y, and z, anywhere there's a z in these functions, we're assuming that we're plugging this function g in for z, so that everything here is just in terms of x and y. Okay? And if you notice, there's no dot product here. The dot product has already been done. What we're doing is we're dotting f with this normal, and you can see that if you compute that dot product, this is exactly what you get. So similar to the case for scalar surface integrals, this is a way which you can skip some steps if your surface is written in a nice way. We can also write this for surfaces where we can solve that equation for the surface for y, or we can solve for x. So if we solve for y, our surface can be represented as a function of x and z. If we solve for x, our surface can be represented as a function of y and z. So the difference here, or the key thing to notice, is that whichever variable you solve for, the corresponding component function is positive and by itself, or it's the same as in the vector field and by itself. And then the other two component functions are multiplied by -1 and multiplied by the partial derivatives of the function that represents the surface. Here, d is a region in the xz plane, dA is dx dz, and in this case, d is a region in the yz plane, and dA is y and z. Now these formulas only work in these special cases. In these special cases as well, you can still do what we did in the last video, parameterize, compute the normal by using the cross product and dotting and integrating. So this is just a way to speed things up, but if it's too much to remember or it's too confusing, you don't have to use this at all. Another thing to keep in mind is we haven't talked about the orientation of these surfaces. So all of these three formulations are assuming that we have a positive orientation of our surface. If you have a negative orientation, you're asked to use a negative orientation for your surface, then you just multiply this formula by -1. Because remember, changing orientation of your surface is the same as multiplying by -1. Okay, let's take a look at an example. So let S be the portion of the paraboloid z equals 4 minus x squared minus y squared above the xy plane oriented upward. Find the flux of the vector field xyz across S. So we're going to parameterize S and find bounds of integration. Well, we can see this surface is already solved for z. So this surface can be represented as a function of x and y, and it's just 4 minus x squared minus y squared. In order to find bounds of integration, I need to know what region I get when I project this surface into the xy plane. So if I draw it, I have this paraboloid, this bowl shape, opening downward, and when I project it, I'm just going to get the widest part of the surface, and the widest part is this circle because it's getting wider as it opens. So the widest part, or what I get when I project, the region is bounded by this circle, which is the intersection of the paraboloid and the xy plane. So in order to find bounds for my region where I want to integrate, I need to figure out what the equation of this circle is. That's going to be the boundary of my region. And so this circle is when z equals 0 and when z is represented by this paraboloid. It's the intersection of these two surfaces, the xy plane and the paraboloid. So I can set up an equation and solve. So if I want z to be on the paraboloid, it's 4 minus x squared minus y squared. If I want z to be in the xy plane, it's 0. So I solve 4 minus x squared minus y squared equals 0. This gives me the circle of radius 2 centered at the origin. So this is the boundary of my region. So the region itself is the disk centered at the origin of radius 2. So that's what I'm going to integrate over. Now if I'm integrating over a disk, it makes sense to convert to polar coordinates. So I'm going to let x and y be r cosine theta, r sine theta. R goes from 0 to 2, theta goes from 0 to 2 pi. And now I need to replace dA with r dr d theta. Now, so I need to make sure I multiply by r. Now this might be confusing because remember when we talked about surface integrals before, I said that computing that surface area element was what you needed. You didn't need to multiply by a Jacobian. But when you use these three formulas, it is assumed that here dA is just dx dy, here dA is just dx dz, and here dA is just dy dz. And that surface area element has already been taken care of. So going from S to D, that's what we get. Now from here, what I'm doing in this example is I'm changing variables again. I'm in the process of setting up this integral, and I'm putting together the information I need to go from an integral over S to an integral over D. But my region D, if I'm using this formula, is assumed to be in the xy plane. So dA is just dx dy. But now I'm deciding to switch from xy, from Cartesian coordinates to polar coordinates. So I'm making a change of variables at this point. I do need to multiply by a Jacobian. So basically every time you change variables, you need to multiply by this change of variables element. Now, we didn't need to do this before because we were just changing from d sigma to dA, or something times dA. And so the parameterization took care of that for you. And usually dA was du dv. And we weren't changing from du dv to something else. But here our dA is dx dy, and we're changing from dx dy to r and theta, so we need to multiply by r. This is something that's subtle, and it can be very confusing, so you really need to work on a bunch of examples and sit with this for a while and understand what the difference is. When do you need to multiply by a Jacobian? When do you not need to multiply? And when is just setting up the problem good enough? Okay, moving on. I need to find the partial derivatives of the function representing my surface. So that was just 4 minus x squared minus y squared. So the partial derivative with respect to x is negative 2x, which when I convert to polar is negative 2r cosine theta. The partial derivative with respect to y is negative 2y, which when I convert to polar is negative 2r sine theta. I need to look at my vector field on the surface. Since we at first assumed that we were in the xy plane, everything needs to be in terms of x and y. So this was my original vector field. I just replaced z with the surface, 4 minus x squared minus y squared. And now since I'm converting to polar coordinates, x becomes r cosine theta, y becomes r sine theta, and z becomes 4 minus r squared. So now this is the vector field I'm going to integrate. When I set up my integral, I'm going to use this formula that we talked about, where now this is my p, this is my q, this is my capital R, and my partial derivatives are given here. And so when I start plugging things in, I have my bounds in theta from 0 to 2 pi, my bounds in r from 0 to 2. Here is negative p times the partial derivative of g with respect to x minus q times the partial derivative of g with respect to y plus capital R times the Jacobian lowercase r. And now I'm just going to multiply everything together, distribute that r to everything. I get 2r cubed cosine squared plus 2r cubed sine squared. So this is just 2r cubed plus 4r minus r cubed. 2r cubed minus r cubed just gives me r cubed. So I'm integrating r cubed plus 4r. I can separate this integral, so that's going to be 2 pi times this integral when I integrate. and then I just integrate, plug in my bounds, get my answer of 24 pi. So that's pretty much it for surface integrals. These problems involve a lot of work. They can be tricky. I suggest doing lots and lots of examples on your own, doing odd problems in the book to check your work to see if you got them correct, asking questions if you get stuck. The only other thing we could talk about are applications of these flux integrals. These flux integrals come up all the time in fluid dynamics, electromagnetism, heat flow, things like that. You see flux integrals all over the place, so there are lots of applications. And for this class, all that's left to cover are Stokes' theorem and the divergence theorem, and then we'll be finished.